Welcome everybody. This is Flow Seminar, where Flow stands for Federated Learning One Word Seminar. That was a seminar created to provide a global online forum for the dissemination of the latest scientific research results in all aspects of federated learning. And today it's my great pleasure to introduce you our speaker, Alexander Tyurin, who is the assistant professor at Skoltech and senior research scientist or team leader at AIRI. In his work, he mainly focuses on modern optimization and machine learning tasks. Previously, he defended his PhD at the Higher School of Economics, and also he was a postdoctoral fellow at KAUST working with Peter Richtarek. And today he's gonna continue our series on the asynchronous methods. Thank you, Sasha, for agreeing to give a talk. Floor is yours.
Thank you. So today I will present my recent work, which I have recently presented also at AIRI. So by the way, can you hear me? Yes, can you see my presentation?
Yeah, all is good.
Yeah.
Yes.
Okay, cool. So I think I'll start with a very quick introduction, motivation, which already was told in this seminar millions of times. So I will be very quick here. So like the first motivation, federated learning. So we consider the problem where we want to minimize some function f, and this function is distributed between some workers, so between computers, laptops, phones, and we want to find the common, some minimum of this function fx, where fx is the minimum of functions fi's. So another related motivation is distributed optimization with GPU and servers clusters. When we have many servers, GPUs, they are either connected through some centralized server or they have some decentralized nature. In general, as I said, we consider a distributed stochastic optimization problem where we want to minimize function f, and function f is the mean of functions of i's. So here we have minimized over x, where x is like in machine learning is a model, and d is a number of parameters in these models or number of features. And here we n is a number of devices or workers, and in federated learning and distributed optimization, we assume that this number is large. It can be 100,000 or even, I don't know, 10,000. And then we assume that each worker has its own dataset di, and each function can be parameterized by dataset di. So first worker contains dataset d1, second d2, and so on. Okay, so in order to present my main topic, I need to start with some things that were already discussed in previous lectures and seminars. And let me quickly remind you what Peter Richtarek told us 2 weeks ago. And I mean, I think it's important for the motivation of my work. So let me start with the problem. So let's start with the following problem. So again, we have n workers, and let's assume that each worker has its own performance. So we assume that the first worker is the fastest worker, and this worker requires tau 1 second to calculate one stochastic gradient. So here the second worker is the slowest one, and this worker requires tau 3 seconds to calculate, like at most tau 3 seconds to calculate one stochastic gradient. And here we have another worker which is requires tau 2 seconds. By the way, if you have any questions, please unmute yourself and just ask me. I don't know, or maybe I think it will be more convenient, I guess. Or you can just post your questions in the chat. Okay, and I will consider non-convex optimization problems. So non-convex optimization problems, we want to find some x such that this inequality holds, but I can assure you that all these ideas, they can be easily extended to convex optimization or strongly convex. But here, for simplicity, I will only talk about non-convex optimization problems. And let me start with homogeneous setting. So homogeneous setting is a setting where I assume that all data set, so where all workers have access to the same data set. So imagine that you, I don't know, train some large language model, and when you train LLMs, you need to sample your data from the internet. And in this case, privacy is not the main concern, so you can just assume that they all sample from the same data set. But then I will quickly go through the setting where through the heterogeneous setting where all workers have contain different data sets locally. Okay, and the assumptions are standard. So like in my talk, I assume that function f is smooth, it is lower bounded, and the stochastic gradients are unbiased and sigma variance bounded. So classical stochastic optimization assumptions from stochastic optimization. Okay, let's start from the beginning, from the simplest case that we have one worker, and the performance of this worker is bounded by some time tau1. So what we know about this setting? We know that actually this is like the classical problem, and we know that like in this paper, it was proved that the number of oracle calls or the number of stochastic gradients that we need to find a solution close to the stationary point is like equals to this formula. So, and we also know that the HDD method, which is the simplest method, one of the simplest methods, actually achieves this oracle complexity, and this method is optimal. And knowing that this is oracle complexity optimal, we can easily get from the oracle complexity we can find easily time complexity. We just can multiply the number of calculate stochastic gradients by the time required to calculate one stochastic gradient. Then we can get that this is the optimal time complexity for the setting when we have one worker with bounded computation time tau1. Okay, is it clear? And it's natural to ask, okay, but what if we have many workers? So, and can we extend the same result to the case when we have many workers and each worker has its own time performance? So I will go quickly through here. That first naive approach that we can consider is mini-batch-GD, when all workers calculate one stochastic gradient, we synchronize them, average them, and then in this case we can show that the time complexity of this approach will be equals to this formula. So once again I refer to Peter's talk that was presented 2 weeks ago, where Peter presented these things in more detail. Similarly, we can analyze another method, asynchronous GD, and we can show that the time complexity of this method looks like this. And then in paper by me and Peter Iftarik, we showed that there exists a lower bound which says that it's possible to design a method that will find solution faster than this time complexity. And this, and then, so we found out that there is a gap between mini-batch GD and synchronous GD and lower bound. And in the end, we proposed a method which we called Reynolds GD. And this method, so actually is so pretty simple. So the idea is that we ask all workers to calculate S stochastic gradients at the same point xk. Then we average them, and then we update our iterate. And then we repeat this procedure t times. Then choosing the right S here under this assumption that the computation times are bounded by T1, T3 to T2, and so on, it is possible to show that Reynolds GD matches this lower bound. So basically, under assumption that each worker has its own computation performance, we close this mathematical problem, optimization mathematical problem. And the similar result actually we can get in heterogeneous sending. So in heterogeneous sending, the difference is that all workers, they have access to different data sets. And then we can propose Malenius GD method, which also optimal and also the complexity of Malenius GD matches the lower bound and up to some constant factor. Okay, so also let me quickly go through another method, ringmaster GD method, which was presented by Arto 1 week ago, or 2 weeks ago. And so this is another approach. So ringmaster SGT, once again, I refer to Arto's talks, but it's just some modification of the asynchronous GT, which makes asynchronous GT optimal. So basically, we prove like that we can slightly modify asynchronous GT, get a ringmaster GT, and then this new method also matches the lower bound. Okay, so and okay, so and we had some other papers on this topic where we analyze different asynchronous GT, but what really bothers here is that all these lower bounds and all these upper bounds and all these comparisons, yes, so when we compare methods here, all these comparisons are done under assumption that each worker, performance of each worker is bounded by some tau y, right? And the question is, okay, but let's say the performances, but in practice, the performances of the workers can vary. So it is possible that at the beginning, this worker, I don't know, requires 3 seconds, then then it requires 4 seconds, 5 seconds, I don't know, then it requires again 3 seconds. So in practice, the performance can vary to different reasons. There can be some reasons due to, I don't know, some like noises in computations, or I don't know, due to partial participation. So the question is like, can we somehow generalize these upper bounds, lower bounds, and can we provide some methodology to compare methods when the computations vary through the time? And so let me introduce one approach how we can do this. And once again, consider the fixed computation model. And the idea is the following. Let's define Vi 1 over Ti. And Vi has a meaning of the power of the worker. So, in this, so here I present 3 plots, and we can see. So let's assign to each worker power. So here, the first worker, the green one, is the most powerful here, and he has the largest power. So the second worker is the slowest one, and here its computation power is smaller relatively to other 2 here. Then we can see that the number of stochastic gradients calculated in the interval is just our power multiplied by t with the floor operation here. So please, I don't know, I think there could be some potential questions here. I don't know, can you please, I don't know, if you have questions, please ask. Okay, is it clear here?
I don't have a question, just kind of a semi-question or comment, or just to engage a little bit. So what you're saying here, that you are basically integrating this constant between 0 and t and then taking floor, right?
Yes. Yeah. Now I will do now, like in the next slide, I will have the real integral operation, but here it's like yes. So it's basically, and So basically, this formula says me how many stochastic gradients this worker can calculate in this interval from 0 to t. So basically, if I substitute here t equal tau I, then I will get 1, right? Which makes sense. If I substitute here t equal to 2 tau I, then I will get 2. And okay, but here we can see that the powers are constant, and the natural idea is to assume that the powers, they vary through the time. And then here we can so here I present 3 examples. So first example is irregular powers, where look here, this first worker at the beginning, it's for some reason is the slowest one, it has the lowest power, and then the power of this worker starts increasing here. Then here it's like at the beginning worker 2 is the fastest one, and then its power decreases. Another thing that can happen here is that pari is periodic. And like my favorite example here is to assume that, okay, here all workers have slow power because it's a day and all students occupied the server. And then here, no, sorry, here it's slow because all students took the server, they run the experiments. But then here it's night, all students went, I don't know, to somewhere, I don't know, went home. And then now, I don't know, I can run my experiments because I get more GPUs and more CPUs here. And this have some periodic nature due to some day-night regimes. Another thing that I can assign is this one is picture which one can see, for example, in federated learning. So look here, the computation power first worker is some positive, and then it becomes 0. For example, assume that it's mobile phone, which is turned on here, then it's turned off, then it again turned on, right? So it's another way how, and computation power is just the like physical nature, which says and just this thing is actually, the idea comes from the physics. So, and in general idea is just for each worker, we assign some computation power, some function, some non-negative function, and that's it. And we can actually it can be even random. So we can just sample it at the beginning, and then it can have some really arbitrarily like random nature. And okay, so now I assigned to each worker, I assigned some power, and then the number of stochastic gradients that like the worker can calculate in interval T1, T0, T1 is the integral of this computation power. And once again, this idea comes from the physics. So recall that the work is just integral of the power. So here it's again, the work that to every worker, so basically computation of the stochastic gradients is the work. And so it makes sense to define the work as the integral of the power. So, and it can be defined mathematically with this formula, looking like this. And in the case when computation powers are constant, then of course one can easily just substitute constant here and show that you will get just Vi multiplied by T, I don't know, T1 minus T0, right? But in general, Vi can be, we can take any like non-negative integratable function and say that in this way we can define the performance of every worker. Okay. Actually, I'm already approaching almost the final and main result. And now the question is, okay, so now I have my assumptions that function f is L smooth, it's low bounded, and I have assumptions about stochastic gradients. And I have this like computation model, right? The question is, what will be the optimal time complexity here? Can we generalize the results, like previous results, to the case, for this formalization? And it turns out like, yes, we can. And let me introduce a lower bound that we can get in homogeneous setting. So unfortunately, unlike the most optimization papers and results, I don't get some fraction. I don't get some really nice formula. And here, the result is slightly implicit. And in order, so basically what this theorem says that it's impossible to converge faster than this thing where like t underline, and this is the index of some sequence here, where this sequence is defined below in the recursive nature. So at the beginning, so like t underline 0 is just 0. Then we substitute this t0 here, and then we can find t1 as the minimum t such that this inequality holds. Then we substitute t1 here, and we have to find t2 for which the minimum t2 for which this inequality holds, and so on. So we can define this like sequence. Then the element with this index is the lower bound, and it's impossible to find the method which would find a point close to the station point faster than this time. So maybe I will quickly show you an example. So again, if I take VIT, my computation powers VI constant, then we can show that this thing is just equals to this. So we can just analytically find this element of the sequence, and we can show that the element of this sequence with this index equals to this thing. And this is exactly the same result that we get with the assumption that the computation. So if I take VI 1 over TI, then we can exactly get this thing here. But okay, another example where it is possible to get explicit formula is to assume that computation powers are some VI multiplied by some GT. And in this case, it's also possible to find some more or less explicit formula. However, like in general, it's it seems like it's really intractable to find it's intractable to find some nice closed formula. And this is I don't know, at least in my case, it's the best result that I could get, and the nicest in some sense result that I could get. And the question, of course, is, so this is lower bound, and the goal, intuitively, I was hoping to show that Renal SGD achieves this lower bound, and yes, it achieves. So again, it is possible to prove, and it's very easy to prove that Renal SGD converges after at most this number of seconds. where bar tk is defined is almost in the same way. And the difference only in some constant factors here. So here I get 24, there I get some C1, here I get C2, here I don't have any constant. But if we ignore these constants C1, C2, and 24, and so on, then the sequences in the upper bound and in the lower bound, they match. And also in the ringmaster, for a ringmaster GD, we can get a similar results. So in this sense, like we can show that Renal GD and ringmaster GD are optimal methods up to constant factors. And this result generalizes a result that we get for the fixed computation model.
So Sasha, I have one comment and one question, if I may.
Yes, yes.
Okay, so one comment, and of course, correct me if I'm wrong. So is it correct to think of the sequence of TKs as follows? So these start with 0 and start increasing. These TKs over bar or whatever you want to call this. And they have the property that the difference between any consecutive TKs is exactly the time needed to collect a mini batch of size max sigma square divided by epsilon and 1 by the workers.
Yes, exactly.
Right?
Actually,
And that's how it's defined. That's how this thing is basically defined, right? That's the definition.
Yes.
Right?
So basically, yes.
And then the idea is that this mini batch size is exactly what even in Renala SGD one would need in one iteration, right? And here, when the times are changing, then is defined in this way because it's still the same mini batch size in one kind of a iteration, right? However, the times are changing, so they have to be defined in this implicit way.
Yes. So basically, maybe what like for analogy D, so we begin. So iteration 0 starts at time t0, and then basically this t1 is exactly the time like when the first iteration stops. So when it finishes. So basically this t. So here, if you look at this sum, so recall that this thing is the number of stochastic gradients that worker I can calculate from this time to t. Here we have the sum. So the sum is just the number of stochastic gradients that they can calculate together. And then we just like in Renal GD, we want to collect the stochastic gradient, the batch size of this, like proportional to this thing, right? So basically, we just wait for the moment, the smallest moment when they will collect this thing, and this will be exactly the moment when the first iteration finishes, and then we start the second iteration.
Okay, so now can you comment? This is the second question where, second, well, this is the second part when I want to ask a question. And the question is, if these times are random, or these powers, worker powers are random, then these times are also random variables, right?
Yes.
And then, so all of these times are random variables, and then how do you then interpret all of this? Because then you say renal SGD converges after at most this time, but this is a random variable. So then you would do what? You would take expectation of it, or what would you do with this result? You just leave it as it is, as a random variable?
I mean, it depends what you want. I mean, it's I don't know, like.
So would you then be able to conclude that this random variable is so would you have a lower bound which is a random variable? So you have a concept of a lower bound that is a random variable and an upper bound which is also a random variable that they match, or how one should think about this randomness in context of optimal methods?
Yeah, okay, I understand the question. So in the context of like lower and upper bounds, I would say that let's say we at the beginning we sample some random performances, right? I don't know, by environment does it for us, right? Somehow.
Yeah.
And then so we take this sample, right? And so some realization.
Yeah. So you have kind of realization optimality or path optimality, right? So it's nothing to do with some probabilistic argument or expectation, anything like this. It's one particular realization of all of this randomness. In respect to that, you're doing optimally.
Yes. So basically, what I mean is that yes, but basically, yes, in this sense, right.
That's even a stronger sense, right? Because it's you get optimal result with respect to any particular realization. One doesn't have to do any averaging or any
Yeah,
kind of
it can be anything. It can
constant.
be even adversarial. So in some sense, so it can be adversarial to your method. So
Okay, good. That's all I'm going to ask.
no, the thing is basically we can. So basically here we have some. So if VIs are random, then we basically just like freeze all the randoms. Sorry, we freeze all the randomness in this VI, and then all these results are like then all these results follow. So I mean then yes. So basically yes, you at the beginning you should freeze these things. So you take some realization, and then you get upper and lower bound. So. Okay, and actually this maybe I will return back to Renals GD. So this work actually was like the main point. Like of course, like there were two goals. At first, to find some like general concept where we can compare methods with where workers can have arbitrary performance, but also of course, like one thing that I tried to show is that Renals GD also is optimal and the method is the same. So basically, and note that the Renals GD doesn't require this VI as an input, so it automatically adapts to this VI. And basically, the only thing that we need is step size here, and we need to tune S. We need to take S proportional to sigma square or epsilon, and then and take gamma one proportional to 1 over L, and then that's it. And then this method automatically becomes optimal for any like computation powers. And it's the same thing actually. So actually, one thing that I tried that I didn't do in the paper, but I tried to do this in presentation is I tried, okay, but let's try and analyze mini-batch GD. Yes, so, and actually for mini-batch GD, we can also show that we can define some sequence, TK, which like, and show that mini-batch GD converges after this number of seconds. So here, once again, TK had the meaning of the number of it's like the time required to finish the case iteration in mini batch GG in this method. And actually, one can show that asymptotically, this thing is, I mean, is worse than the result that we get with Reynolds GT. Okay, and similar result, it's possible to get in heterogeneous setting, and the idea is similar, but the only difference is here, instead of the, like, if you here, instead of the mean of VI, like, we somehow, for some reason, I get harmonic mean. So this TK is defined this recursive way where everything almost the same, but here we have some like other dependence on this VI on the VI on the computation work here. But the idea is the same, that we can show that this is the optimal time complexity, and it's achieved by like Malenius GD method. And maybe let me summarize. So like in the previous papers, what was done is that like we analyze mini-batch GT, we analyze synchron GT, we analyze Reynolds GT, and under the assumption that the time required to calculate one stochastic gradient bounded by tau I. Basically, in this work, what was done is like what I tried is to extend these results to the case when computation vary through the time, and the idea was to assign to each worker some computation power, and then we can compare methods. So instead of comparing these quantities, we compare methods using these quantities. Yes, unfortunately, it's less convenient, and it's very not, I would say, not convenient to compare methods using these things, and the problem is here that the computation powers can be arbitrary, so it's arguably infeasible to find really nice explicit formulas. But it's so that's what was done here, and I think actually in general there's a correlation between like previous. So actually, like the fixed computation model is quite like good model in order to compare methods. So we can see that like if at least for these four methods, if fixed computation model is better in one method than in another, then its universal computation model also is better than in previous one. So if you want to, I don't know, if you've, let's say, developed some asynchronous method, then I think if under the fixed computation model you're better than another method, then very likely that even in general case for the universal computation model, it also will be better. So
I'd like to ask another question. This may actually be an idea for research. Just came to me now when you presenting this slide. So would it be possible to do the following? So to actually have a reduction of the type that you were suggesting might exist. Because if you look at the universal computational model, then the argument basically there is that you need to define this recursive sequence, but the idea of the recursion always is collect a big enough mini batch size, right, in that one iteration, and that mini batch size is exactly what you would collect in the fixed computational model if you fixed those times, and they are fixed in that I mean, one can even think that they're kind of fixed in that interval, right? Or maybe, you know, you average it in that interval, something like that. So would it be possible to do the following? If that one proves complexity in the fixed computation model, and then argues that as soon as you do it in the fixed computation, and maybe it's enough to do it basically just for collecting one mini batch, or basically doing this one step. And then one would argue that if the method has optimal complexity there, it would have optimal complexity in the universal computation model.
No, I mean, I know one
So be
counterexample.
reduction rather than
I know this
rather
one
than reproving it.
No, I think I know one counterexample. It's this. Remember this naive optimal ISGD in the ringmaster paper. So this naive method is optimal under fixed computation model, right?
Yeah.
But under universal computation model, it is not optimal because I mean, recall it's in this.
Yeah. I mean, I understand this. So, I mean, I overshot a little bit the desire because, of course, in that time frame between, let's say, TK and TK plus one, the computation times of any worker can change even many times, right? And then if a method is not aware of that, then things can go wrong. But um, I mean, some sort of reduction. So this precise reduction will not work, as you just confirmed. But some sort of reduction, just because of the very clear similarity between these two approaches. That this whole idea is to just collect enough stochastic gradients in the time and define the time as being whatever you need to collect enough, right? So somehow that is the important thing. It's not the computation dynamics or any of this. It's just the mini batch size. That's all that matters, right?
Mm-hmm. Mm.
So basically, if you have a method which let me put it differently. If you have a method which collects this mini batch size in as fast way as possible, should be optimal, right? Something like that.
No, I mean it's like you said, if if method collects as fast as possible, then it's optimal. It's like saying the method is optimal if it's optimal. Something.
No, it's not. It's not the same thing because somehow uh, it just turns out somehow that it's enough to just be iteratively collecting mini batch size of psi sigma squared of epsilon, let's say, okay, if these methods are these semi-asynchronous methods. Somehow it turns out that that idea, which may look naive, is the optimal idea. That don't worry about the computation dynamics, just worry about collecting mini batch size of psi sigma square of epsilon, and whatever time it takes, just take that time. So basically, that's the prescription here, right? And pay that price, and that happens to be the optimal thing. And I'm asking whether this kind of a prescription can be formalized, perhaps even outside of any particular algorithm that achieves it, right?
Mm-hmm.
So this is not, very clearly yet spelled out, the idea, but I hope you get at least the idea. So there is something here which seems to be unexplored of this type, right? Because this result seems to be implicit in all of these complexity results, that you just collect this mini batch size and pay whatever price you're gonna pay. And but none of those results seem to be written that way. That's what matters, right? So one can maybe abstract even away one layer of abstraction and say that's exactly what's going on. Just pay whatever price you need to pay to collect this mini batch size, and that will happen to be optimal. Okay, so this was like one thing that I wanted to ask. I want to give chance to others because I'm taking too much time. But I have one more question. If at the end there'll be room, then I'll ask one more question. Thank you.
Actually, that's it. So please ask questions. So that's all that I wanted to say.
Yeah, I'll be just quiet until the very end, and then maybe ask if there's
Okay,
room.
there's some message. How would fully synchronous? Okay, so I don't know if so basically I presented, so I said that Renal converges like, so in this, so okay, so maybe I didn't stress it enough, but actually like in Ringmaster GD, we proved a similar result where we showed that we also get similar recursion up to constant factors. So we can show that Ringmaster or ISGD also optimal. So in the universal computation model, I don't know. So Amar, so have I answered to a question? I hope so. Okay.
Yeah, thank you, Sasha, for the talk. This is going to be another question, but maybe a comment about the heterogeneous setting result you got. So you said that for some reason you got the harmonic mean instead of the small result for the homogeneous setting. And I'd probably say that maybe it's very nice that you got harmonic mean, because in this case, the case when, say, a worker shuts down and never participates in the training essentially means that the algorithm won't converge. And harmonic mean captures this case.
Yes. I mean, so if one of these workers doesn't participate, then this thing here, you can show that it's just always zero. So it is necessary that all workers participate. It's not sufficient, but it's necessary. While in homogeneous setting, you don't need all workers. And this captured here. Yeah, so basically, I'm not sure it was the question. It's just I think it's just a comment, right?
Yes, it's just a comment. That's a nice
Yes.
thing about this result.
Yeah, once again, if you substitute here, like if you substitute here, if you assume that powers are constant, then you will exactly get the same result as in like that your time complexities depend on the mean. So, and also depend on the slow, in one term it depends on the slowest work, and then in stochastic term it depends on the mean. So,
Hi, Sasha. Thank you for the talk. Yeah, I'm wondering, you mentioned at some point that everything can be generalized to the convex case as well. Also, I guess the method itself can be replaced, like you make an SGD step, but of course one can apply this idea of collecting the right mini batch and then making, let's say, applying some other method, like you can maybe apply accelerated method. But in the convex case, for accelerated methods, you need to use larger batch size, but you do in the end fewer number of steps. So, like, does it mean that if you apply this technique in the synchronous regime, that instead of, for example, sigma squared over epsilon, you will have like sigma squared over epsilon to the power 3 over 2 if you apply on top of that accelerated method?
yes. So basically, you will get one deterministic term, one stochastic, and then the stochastic term, it like inversely proportional to batch size, right? And then you just need to choose B such that deterministic term is equal to stochastic. And this seems like universal rule for I don't know, convex, non-convex setting. Yeah.
Is there any
And
case? Oh, yeah, sorry.
yeah, what any case?
Yeah, I'm just curious, like perhaps under some, like if this function vi changes in some weird way, maybe I don't know, maybe in some cases would be beneficial to use non-accelerated method. I mean, from theoretical perspective, because for accelerated method you need to wait longer, and if VIT, I don't know.
I understand the question.
So perhaps you can, like, I don't know, switch between the methods in the beginning. Or for example, you can identify some regimes when VIT
No.
is.
I mean, I think accelerated will always better. I mean, because wait.
For example, like can be the case that VIT is somehow like the power decreases over time. So maybe at the beginning it's much better to.
No, asymptotically. So am I right that the batch size? No, batch size in the accelerated version will be larger than in non-accelerated, right?
Yeah, if you are talking about convex case, yes.
Yes. No. No. It's always will be accelerated will always better because no. I mean it's asymptotically. No, it will be always better because actually. Ideally, we just want to, I don't know, the larger the batch size, the more we can take from parallelism. So, I mean, what I'm trying to say is that let's say I have millions of workers, right? And I want to calculate batch size of 10, right? Then, I mean, I don't need millions of workers, right, for that. But if I have millions of workers and I want to calculate batch size of 10 million, right? Then I can better utilize these workers, right? So I mean I think it's not difficult. Okay, 99% think that we can show that accelerated is better because it takes less iterations and there's nothing wrong with the fact that the batches are large. I think it's actually it's nothing wrong here. At least right now, I don't see any problems. Like
Yeah, for me, I agree with you when, for example, the power is constant for each worker, stays constant. Then, yeah, but it's not that at least trivial for me right now to see that in the for arbitrary power like function.
so I think asymptotically it will be always better. So
Yeah, but anyway, thank you for your answer. It's really
uh,
interesting.
Are there any other questions? I think we still have some time.
Should I ask now if nobody's asking?
Please go ahead.
Okay, so there seems to be some, at least superficial at the moment, similarity between what's going on in here, and it's not necessarily related to this universal computation model. Could even applies what I'm going to say to the fixed computation model. And what I'm trying to say is there's something similar going on here, which we can see in the literature on Byzantine robustness. And my question is, can this lead to something, to some new discoveries? And what I'm trying to say is this. In Byzantine robustness, you have n workers. Here we have n workers. And Byzantine robustness, some workers are malicious and they just send bad stuff. So not actually the stochastic gradient they're supposed to be sending, but just some nonsense. And the server is trying to figure out who they are and ignore progressively these kinds of updates because they would just prevent the algorithm from converging. So here, everybody's sending the correct stochastic gradients, but they are kind of bad because some of them arrive too late. So they're not bad because the stochastic gradient is bad, but because it just arrives too late. And the server learns to ignore them because they arrive too late. So for instance, in a ringmaster, there's this delay threshold, and this delay threshold basically can be thought of some sort of delay robust aggregator, right? You aggregate, but you ignore the slow ones. So is there the question here is maybe there is some kind of an yet undeveloped theory of robust distributed optimization, which would interpolate these cases. Because maybe in Byzantine robustness, stuff can be arbitrarily bad. Here, only the time can be arbitrarily bad, but maybe there is some kind of interpolation in between where other things can be bad and so on. And there could be, I don't know, maybe an exchange of ideas between these two fields, but maybe even a universal approach to both problems. I mean, I don't expect an answer here. It's just a,
Yeah, I won't provide an answer because I don't know.
Yeah, this is just an idea that occurred to me. So I think this might be potent thing to explore. And I also had another one, but time is up and I need to go and meet with Shuin, who is here in the audience. So thank you very much, and I'll be leaving now.
Okay. Thank you for the participation.
Right. Yeah. Thank you, Sasha, for a very nice talk. And yeah, if nobody has questions, then yeah. Thanks all for attending, and hope to see you in the next flow talk that's going to be soon announced. Thank you all. Have a great rest of the day. And Sasha, please just send me your slides and I'll post them along the recording.
Okay.
Thank
Thank you.
Bye-bye.
Bye-bye.